tonight, we're going to explore the coldest places in the universe. You already know cold. You have felt it while stepping outside before sunrise. You have wrapped yourself inside a blanket after a long winter evening. You have watched warm breath become pale mist. Those moments feel cold because your body notices every degree that slips away. Yet every cold memory on Earth belongs to a world overflowing with warmth. Space tells a different story. There, warmth is the rare visitor. Cold is the ancient resident. By the end of tonight, you will understand why the universe is not remembered by its brightest stars, but by its oldest silence. You will discover why the deepest cold is not simply the absence of heat. It is the memory of time itself. Imagine placing your hand upon a wooden table. It feels cool. Not because the table creates cold. It merely accepts warmth from your skin more quickly than air. Your fingers surrender tiny packets of energy. Molecules vibrate less enthusiastically. Your nerves quietly report the change without thinking. You pull your hand away. Every human has repeated this small experiment thousands of times. We spend our lives exchanging warmth with everything around us: the air, the ground, a cup of tea, a sleeping pet. Another human hand. Heat always moves, always flows, always searches for balance. That simple truth follows us far beyond Earth. The universe obeys exactly the same rule. Yet once we leave our familiar atmosphere, balance becomes almost impossible to find. Earth seems cold during winter. Antarctica may fall below -90 degrees Celsius. High mountain summits steal heat from exposed skin within minutes. Arctic winds freeze lakes into solid mirrors. These places seem merciless. They inspire explorers to layer clothing. They build shelters against invisible enemies carried by moving air. But compared with space, even Antarctica resembles a warm fireplace glowing beneath a quiet roof. Our planet wraps itself inside a protective blanket. The atmosphere captures energy from the sun. Oceans slowly release stored warmth each night. Clouds scatter infrared radiation. Winds endlessly transport heat from one continent to another. Earth never truly stops breathing warmth, even beneath polar ice. Tiny organisms survive. Liquid water hides beneath glaciers. Volcanoes continue whispering beneath ancient rock. The planet remains alive because energy never fully disappears. Step beyond this protective shell. Everything changes. There is no comforting air surrounding your body. No breeze, no clouds, no forests absorbing sunlight. Only darkness. Endless darkness. And silence so complete it almost feels physical. At first, this seems impossible. We often imagine space as burning. Stars blaze brilliantly. Galaxies sparkle across impossible distances. Supernovas briefly outshine entire galaxies. Black holes unleash astonishing jets. Everywhere we look through telescopes, brilliant light floods photographs with color. Yet those spectacular images hide an important truth. Almost all of the universe is not inside stars. Almost all of it lies between them. The immense emptiness separating those islands of fire remains unimaginably cold. If someone could drift safely through interstellar space, they would not feel a freezing wind. There is no air to carry one. They would simply continue losing warmth. Slowly, relentlessly. Their own body would radiate energy outward. Nothing nearby would return it. The exchange always favors the darkness. This idea feels strangely familiar. Imagine sitting beside a campfire at night. Every step away from the flames changes almost nothing at first. Then another step, another. Soon the warmth fades. The fire still burns exactly as before. Yet its influence weakens. Distance quietly steals comfort. Space behaves much the same way. Every star resembles a lonely campfire surrounded by an ocean larger than imagination itself. The fires shine, but between them stretches an endless wilderness where warmth rarely travels far enough to matter. Even our sun cannot protect the entire solar system equally. Mercury bakes beneath fierce sunlight. Earth enjoys a narrow band where oceans remain liquid. Jupiter receives only a fraction of Earth's warmth. Neptune circles 30 times farther away. Sunlight there becomes a faint memory. Beyond Neptune, sunlight resembles a bright star rather than a comforting source of heat. Yet, even those frozen worlds still belong to our cosmic neighborhood. The true universe extends vastly farther. Here, another surprising realization appears. Cold itself is invisible. We cannot see it. We notice only its consequences: frost upon glass, ice across ponds, slower movements, sleeping forests, fading breath. Likewise, the universe rarely announces its cold directly. Instead, astronomers discover it through subtle clues: molecules rotating more slowly, infrared light fading, clouds absorbing faint radiation. Sensitive instruments reveal what human eyes never could. Modern observatories have become extraordinary thermometers stretching across the cosmos. They detect temperatures separated by fractions of a degree. They measure invisible wavelengths, gently arriving after journeys lasting millions or even billions of years. Every observation tells another chapter in the universe's quiet autobiography. Every measurement whispers how energy moved, where it remained, where it disappeared. Yet perhaps the most remarkable discovery is not that space is cold. It is that the universe has been cooling almost since its birth. Long before Earth formed, before the sun ignited, before galaxies assembled their graceful spirals, the cosmos glowed with astonishing heat. Matter itself behaved differently. Light scattered constantly. Nothing resembled today's peaceful night sky. Time transformed everything. Expansion stretched space itself. Temperatures slowly declined. The blazing infancy of existence matured into a calmer adulthood. That cooling continues even now. Every passing second carries the universe towards slightly greater stillness, slightly lower temperatures, slightly longer echoes. This journey unfolds so slowly that no single lifetime notices it. Humanity lives inside one quiet frame of an unimaginably long film. We inherit a universe already cooled from impossible beginnings, yet still slowly surrendering tiny fragments of warmth into eternity. There is something deeply comforting about this realization. We often fear change because it feels sudden. Seasons arrive unexpectedly. Loved ones grow older before we notice. Cities transform. Memories soften. But the greatest transformation ever witnessed unfolds almost beyond perception. The entire cosmos changes with breathtaking patience. No hurry, no panic, only endless drifting, endless cooling, endless unfolding. Perhaps that is why the night sky often feels peaceful instead of frightening. We unconsciously recognize this rhythm. Stars rise, stars set. Winter follows autumn. Morning follows darkness. Heat becomes memory. Memory becomes silence. Silence becomes the beginning of another story. And tonight, our own journey has only taken its very first step. We have learned that Earth's coldest winters belong to an unusually warm world. We have discovered that darkness alone does not define space. Temperature does. Yet an even deeper mystery now appears before us. If heat always flows away, where does it actually go? Why has the universe spent nearly 14 billion years quietly surrendering its warmth instead of keeping it forever? The answer begins with something so ordinary that most of us overlook it every single morning. A cup of coffee resting quietly upon a table. The coffee is too hot to drink. Steam rises in delicate ribbons. The mug warms your hands. For a brief moment, it feels alive. Then, almost without notice, the steam becomes thinner. The surface grows still. One careful sip no longer burns your tongue. Another few minutes pass. Eventually, the coffee reaches the same temperature as the room. It never becomes hotter by itself. It never gathers lost warmth and returns to its original state. The journey always moves in one direction. Heat leaves. Silence follows. This quiet event happens every day. It seems too ordinary to deserve attention. Yet, hidden inside this familiar scene is one of the deepest rules governing the universe. Physicists call it the second law of thermodynamics. The words sound intimidating. The reality feels surprisingly gentle. Energy prefers to spread out. Warmth seeks balance. Differences slowly disappear. A hot object cools. A cold object warms. The universe quietly smooths every sharp contrast. Imagine dropping a single drop of blue ink into a clear glass of water. At first, the color remains concentrated. Then, delicate streams appear. Tiny swirls drift outward. Soon, the entire glass becomes softly blue. You never watch the ink gather itself again into one perfect drop. Nature always favors the wider distribution. Heat behaves in much the same way. Instead of color spreading through water, energy spreads through matter and light. It drifts outward. It becomes less concentrated, less useful, less dramatic. This gradual spreading has a name: entropy. Entropy is often misunderstood as chaos. It is better imagined as fading contrast. Think of footprints in fresh snow. At sunrise, they appear sharp and clear. Hours later, the wind softens their edges. Another snowfall nearly erases them. Eventually, no trace remains. Nothing magical happened. Information simply spread into countless tiny changes. The universe gently blurred the picture. Heat follows the same quiet path. When the sun shines upon Earth, its energy arrives highly concentrated. A single square meter receives hundreds of watts under clear skies. Plants gather it. Oceans store it. Animals eat because of it. Human civilizations rise because of it. Yet none of that energy stays forever. Every sunset begins another slow release. Roofs cool. Forests cool. Oceans radiate invisible infrared light toward the sky. Throughout the night, Earth quietly returns borrowed warmth to space. Even now, while you listen, billions upon billions of infrared photons are leaving our planet every second. They travel upward without sound. Most never return. They continue into the darkness between worlds. This exchange has continued for billions of years. Without it, Earth would become dangerously hot. With too much of it, Earth would become a frozen desert. Life exists because the balance remains remarkably delicate. Yet space itself receives this escaping warmth without complaint. It does not grow noticeably warmer. The reason lies in its astonishing size. Picture lighting a single candle inside an enormous cathedral. Nearby, stones glow softly. Walk farther away. The warmth disappears. The candle still burns. The building simply contains too much empty space for one flame to matter. Our sun resembles that candle. The solar system resembles the cathedral. The galaxy resembles an entire continent. Distance quietly defeats warmth. This realization begins to reshape how we imagine the night sky. We often think stars dominate the universe because they are bright. In truth, brightness occupies remarkably little volume. Nearly everything between those lights remains astonishingly empty. The darkness wins, not through force, but through patience. Scientists measure temperature using the motion of particles. Hot molecules move rapidly. Cold molecules drift more slowly. At absolute zero, defined as 0 Kelvin, particles possess the least possible thermal energy allowed by quantum mechanics. Absolute stillness, however, remains impossible. Even the emptiest vacuum carries tiny fluctuations. Reality itself refuses perfect silence. Absolute zero therefore acts like a distant horizon. We may approach it. We never quite arrive. The coldest laboratories on Earth have cooled atoms to astonishingly tiny fractions above absolute zero. Researchers used lasers and magnetic fields. At those temperatures, matter behaves almost like a single giant quantum wave. Strange effects emerge. Atoms lose their individual identities. Entire clouds move together as though sharing one quiet thought. These experiments reveal something profound. Cold is not simply the opposite of heat. Cold reveals hidden layers of reality, usually concealed by constant motion. The universe performs similar experiments naturally. Vast molecular clouds, dark nebulae, remote regions between galaxies. Everywhere heat becomes scarce, new behaviors quietly appear. Yet there remains another way for energy to travel. Not through touching, not through moving air, but through light itself. Stand beside a fireplace. Even before the warm air reaches you, your face begins to feel comfortable. Invisible infrared radiation crosses the room almost instantly. The fire sends energy without needing physical contact. The sun warms Earth the same way. Empty space carries electromagnetic waves with perfect efficiency. This process never stops. Every object warmer than absolute zero continuously radiates energy. You do it. The chair beneath you does it. The walls do it. Entire galaxies do it. Even the faintest grain of cosmic dust quietly shines in infrared wavelengths. The hotter the object, the more energetic the radiation becomes. A blacksmith's iron glows red. Heat increases further. Orange appears. Yellow follows. Eventually, blue-white light emerges from the hottest stars. Their color reflects temperature. The universe paints itself using thermal physics. Yet after emitting light, every object loses a little energy, a little warmth, a little memory of its previous state. Given enough time, everything cools unless another energy source intervenes. Stars avoid rapid cooling because nuclear fusion continuously replaces lost energy. Their immense gravity crushes hydrogen into helium. Tiny amounts of mass become tremendous amounts of light. This invisible furnace has sustained our sun for over 4.5 billion years. But even stars possess limits. One day the hydrogen diminishes, fusion slows, the balance changes, the long cooling begins. Entire stellar lifetimes become stories about delaying the inevitable escape of heat. This truth reaches even farther. Galaxies collide, black holes consume matter, planets form, civilizations rise. Every spectacular event briefly concentrates energy before allowing it to spread once again. Fireworks explode brilliantly because they release stored chemical energy. Supernovas dazzle because collapsing stars suddenly redistribute unimaginable reserves of heat and light. Beauty often accompanies imbalance. Stillness follows equilibrium. Perhaps this explains why sunsets feel peaceful. During the day, sunlight creates powerful contrasts. Bright shadows, warm pavement, shimmering air. Evening softens them all. Colors fade, temperatures drift together. The world slowly approaches balance. The universe performs an endless sunset, not over hours, not over centuries, but across trillions upon trillions of years. Every passing moment becomes another almost invisible step toward quieter conditions. Astronomers sometimes describe this distant future as thermal equilibrium. Energy will still exist, matter will still exist. Space will remain unimaginably vast, yet dramatic differences will become increasingly rare. The cosmos will resemble an ocean after every wave has finally settled. Fortunately, that future lies almost beyond comprehension. Humanity exists astonishingly early in cosmic history. Stars still shine. Galaxies continue forming new generations of suns. Nebulae glow with possibility. The universe remains vibrant precisely because enough warmth still survives. We are living during one of its brightest chapters. That thought carries unexpected comfort. You and I exist during an age when the sky still sparkles, when stars still forge new elements, when planets still form, when warmth still gathers around islands of light. Someday those islands will become fewer. Their campfires will gradually fade. The darkness between them will grow even quieter. Yet before the universe reaches that unimaginably distant future, we must first cross the immense spaces already existing today. Spaces so empty that even light seems lonely. Regions where galaxies themselves appear like distant lanterns floating across an endless frozen sea. That silent ocean awaits us next. The quietest place many people ever experience arrives just before dawn. The streets remain empty. The wind has settled. Even birds hesitate before beginning their morning songs. You step outside. The air feels cool. Every sound seems farther away. The world appears larger simply because so little is moving. It is a peaceful silence. Yet, it is still surrounded by life. Houses breathe with hidden warmth. Trees hold sleeping animals. Beneath your feet, millions of tiny organisms continue their invisible work. Now imagine removing every house, every tree, every mountain, every planet, even every nearby star. The silence becomes something entirely different. This is the space between galaxies, not merely empty, almost unimaginably empty. Our minds naturally underestimate distance. Looking into the night sky, stars appear sprinkled across a flat ceiling. They seem close enough to form familiar shapes. Orion raises his arm. The Big Dipper points north. Cassiopeia rests upon her celestial throne. Yet those patterns exist only because our eyes compress depth into a single view. Reality stretches far beyond ordinary intuition. Even within our own galaxy, neighboring stars remain separated by astonishing distances. If our sun were reduced to the size of a small orange, the nearest star would still rest thousands of kilometers away. Almost everything between them would contain almost nothing. Leave the Milky Way behind. The distances become almost impossible to picture. Galaxies themselves become isolated islands. Each one contains hundreds of billions of stars, yet they float across oceans so vast that their nearest neighbors often lie millions of light years away. Imagine standing upon a tiny island in the Pacific Ocean. The nearest coastline disappears beyond every horizon. The sea surrounds you completely. Now enlarge that image until each island becomes an entire galaxy. The ocean becomes intergalactic space. Even this comparison remains too small. Because oceans contain water, intergalactic space contains almost nothing at all? Scientists estimate that, in many regions between galaxies, only a few atoms occupy an entire cubic meter. Some places contain even less. A box large enough to hold a washing machine might possess fewer particles than a laboratory vacuum chamber. Those lonely atoms drift through darkness for millions of years before encountering another. Motion still exists. Gravity still acts. Light still travels. Yet matter itself becomes extraordinarily rare. This emptiness creates remarkable consequences. Without nearby stars providing continuous warmth, temperatures remain astonishingly low. The only significant source of heat comes from an ancient glow filling every direction equally. It is weak, gentle, almost perfectly uniform. We will meet that ancient light soon. For now, simply know that even complete darkness is never entirely empty. Light continues crossing these immense regions, patiently, relentlessly. A single photon leaving one galaxy may travel for billions of years before reaching another. during that unimaginable journey. It passes almost nothing. No planets interrupt it. No dust clouds significantly slow it. No atmosphere scatters its path. It simply continues. The universe becomes less like a crowded city, more like a solitary traveler crossing an endless frozen desert. This image carries another surprising truth. Galaxies themselves are moving apart, not because they race through space like airplanes. Space itself slowly expands between them. Imagine tiny dots drawn upon the surface of an inflating balloon. As the balloon grows larger, every dot observes the others drifting away. None of the dots actively crawl across the rubber. The surface itself stretches. Our universe behaves similarly. Since the Big Bang, space has continued expanding. That expansion gently increases distances between galaxy clusters. Light crossing those widening gaps gradually loses energy. Its wavelength stretches. Astronomers call this cosmological redshift. Picture playing a familiar melody on a piano. Now imagine slowly pulling the piano strings longer while each note continues ringing. The pitch falls. The sound deepens. Something similar happens to light. Its color quietly shifts toward longer wavelengths. Its energy gently decreases. Expansion itself cools the universe. This process has continued for nearly 14 billion years, without drama, without noise, simply stretching, always stretching. Every expansion slightly weakens ancient radiation left from the universe's fiery youth. Every billion years adds another almost invisible layer of cooling. This is why distance and temperature remain deeply connected. The larger the universe becomes, the colder its average background grows. Intergalactic space therefore acts as an enormous archive. It remembers expansion. It remembers ancient heat. It remembers beginnings that no human could ever witness directly. Astronomers study this emptiness with extraordinary care. Powerful telescopes do not merely search for bright galaxies. They also examine what lies between them. Sensitive instruments detect faint hydrogen gas. They measure subtle absorption lines. They observe distant quasars whose brilliant light passes through nearly invisible clouds during journeys lasting billions of years. Every tiny shadow reveals another hidden structure. Every faint signature tells another chapter of cosmic history. Recent observations continue refining this picture. Modern telescopes map enormous filaments connecting galaxies across staggering distances. These delicate strands compose what scientists call the cosmic web. Galaxies gather where invisible dark matter provides additional gravity. Between those filaments stretch enormous voids. Some voids span hundreds of millions of light years. Imagine removing nearly every city from an entire continent, then removing almost every village, then leaving only a handful of isolated lights. The remaining darkness begins approaching the emotional scale of these cosmic voids. Yet even they are not perfectly empty. Quantum physics quietly refuses perfection. Tiny fluctuations ripple through the vacuum itself. Virtual particles briefly appear and disappear. Space never becomes absolute nothingness. Instead, it resembles a calm sea whose surface remains almost perfectly still, while microscopic ripples continue beneath. This subtle activity reminds us of something beautiful. Silence is rarely absolute. Stillness always contains hidden motion. A sleeping forest continues growing. Snowflakes slowly settle. The ocean quietly shifts beneath calm waves. Likewise, intergalactic space never truly sleeps. Gravity patiently reshapes enormous structures. Light patiently crosses impossible distances. Expansion patiently stretches reality itself. Perhaps patience is the defining quality of the cosmos. Human history measures thousands of years. Civilizations rise and vanish. Languages appear. Empires dissolve. Yet during all those centuries, a single beam of light crossing intergalactic space barely notices our existence. It continues exactly as before. Entire human lifetimes become less than a heartbeat along its endless journey. There is no insult in that realization, only perspective. Our lives remain precious precisely because they unfold within limited time. The universe teaches patience because it possesses almost unlimited time. Its frozen spaces remind us that waiting need not feel empty. Sometimes waiting becomes the story. Sometimes silence carries memory more faithfully than sound. As we drift farther from familiar stars, another remarkable discovery slowly approaches. We have crossed immense darkness. We have learned that nearly empty space quietly preserves the history of expansion itself, yet something still fills every direction. No matter where astronomers point their instruments, no matter how distant the galaxy, no matter how empty the void, a faint glow always remains. It does not come from nearby stars. It does not come from galaxies. It arrives from a time before either existed. The coldest reaches of space are not completely dark. They are illuminated by the oldest light in existence, a whisper still traveling from the birth of everything. The softest light in your home often comes after every other lamp has gone dark. A tiny digital clock glows beside the bed. Moonlight slips quietly through a curtain. The hallway casts a faint line beneath the door. None of these lights ask for attention. They simply remain. Gentle, patient, almost forgotten. Now imagine discovering that the entire universe possesses a similar glow, a light so ancient that every galaxy, every star, every planet has lived beneath it. A light that reaches us from a time before the first sunrise ever existed. This is the cosmic microwave background. Astronomers often shorten its name to the CMB. It surrounds us completely, above your head, beneath your feet, beyond every constellation, beyond every galaxy. No matter where we look, it quietly waits. Its temperature measures only about 2.7 Kelvin, barely above absolute zero. Yet, this extraordinary cold is not evidence that nothing happened. Quite the opposite. It is the faded warmth of everything that happened first. Imagine removing every city from Earth, every forest, every mountain. Leave only the atmosphere itself. If someone could somehow listen to the remaining air, perhaps they might still detect echoes from storms that passed long ago. The atmosphere remembers movement. The universe remembers heat. Nearly 14 billion years ago, the cosmos looked nothing like the peaceful sky above us tonight. There were no stars, no planets, no galaxies drifting through darkness. Instead, everything existed inside an astonishingly hot sea of energy. Temperatures reached trillions upon trillions of degrees. Matter could barely hold itself together. Light constantly collided with charged particles. Every direction glowed with unbearable brilliance. There was no darkness, only light, only heat, only motion. If you had somehow appeared during those first moments, you would not have seen across a room. Light itself struggled to travel freely. Every photon immediately scattered from countless particles surrounding it. The universe resembled an endless glowing fog. Then something remarkable began. Expansion. Space itself continued growing larger. As it expanded, everything inside spread farther apart. Energy became less concentrated. Temperatures slowly declined. Minute after minute, century after century, hundreds of thousands of years passed. Eventually, the universe cooled enough for electrons to combine with atomic nuclei. Neutral hydrogen formed. Suddenly, light no longer scattered constantly. Photons escaped for the first time. The fog lifted. The universe became transparent. Those ancient photons still travel today. They have never stopped. Imagine writing a letter and placing it into a bottle. The bottle drifts across an immense ocean for thousands of years before someone finally discovers it. The paper has aged. The ink has faded. Yet, the message survives. The cosmic microwave background resembles that bottle. It carries information from an unimaginably distant past. The light reaching our telescopes tonight began its journey when the universe was only about 380,000 years old. Compared with today's age of nearly 13.8 billion years, that was cosmic infancy. Because space continued expanding during those billions of years. The photons themselves stretched. Their wavelengths grew longer. Their energy gradually declined. Light, once brilliant enough to resemble the surface of a hot star, slowly transformed into faint microwave radiation. The universe did not extinguish its first light. It gently cooled it. This subtle transformation explains why the background temperature now rests near 2.7 Kelvin instead of thousands of degrees. Expansion acted like an invisible musician, steadily lowering every note in an endless symphony. The melody never stopped playing. It simply became deeper, softer, slower for centuries. Humanity had no idea this ancient glow existed. Our eyes cannot see microwaves. Ordinary telescopes could not detect them. Only in the 20th century did technology become sensitive enough to uncover this quiet whisper. The discovery itself arrived almost by accident. Two radio astronomers, Arno Penzias and Robert Wilson, were carefully calibrating a sensitive antenna. No matter where they pointed it, an unexpected background signal remained. They cleaned the instrument, they checked the electronics, they even removed nesting pigeons and their droppings from the antenna. Wondering whether something ordinary caused the mysterious noise, nothing changed. The faint hiss persisted. Eventually, scientists realized they had stumbled upon one of the greatest discoveries in modern cosmology. They were hearing the oldest light in existence. Even today, if an old analog television loses its broadcast signal, a tiny fraction of the static, once visible on the screen, originated from this ancient radiation. Most interference came from other sources, but a small portion truly represented photons that had traveled since the universe's earliest transparent age. The idea feels almost impossible. Ancient light quietly entered millions of living rooms, not as a spectacular beam, not as a brilliant star, but as barely noticeable static. Modern spacecraft transformed this discovery into detailed maps. Missions such as COBEWMAP and Planck measured the cosmic microwave background with astonishing precision. They revealed that it is remarkably uniform. Nearly every direction shares almost exactly the same temperature, yet not perfectly. Tiny differences exist, only a few millionths of a degree. Those minute variations became the seeds of everything familiar today. Slightly denser regions possessed a little more gravity. They slowly attracted additional matter. Over immense spans of time, those tiny irregularities grew into galaxies, galaxy clusters, stars, planets, even ourselves. Imagine baking bread. The dough appears smooth, yet tiny bubbles form inside. As the loaf rises, those tiny differences become the structure of the finished bread. The early universe behaved similarly, almost perfectly uniform, yet not completely. Those microscopic imperfections became every mountain, every ocean, every tree, every heartbeat. There is extraordinary comfort hidden inside this realization. The galaxies did not appear despite those tiny fluctuations. They appeared because of them. Imperfection became creation. Small differences became infinite beauty. Recent observations from modern observatories continue refining our understanding of the early universe. Powerful instruments, including the James Webb Space Telescope, have revealed surprisingly mature galaxies existing earlier than many expected. These observations have encouraged astronomers to improve models describing galaxy formation and cosmic evolution, yet they do not erase the fundamental picture provided by the cosmic microwave background. Instead, they enrich it. Observation continues. Interpretation evolves. The ancient light remains one of the strongest foundations of modern cosmology. The universe therefore behaves less like a completed book and more like a manuscript still being carefully read. Each generation notices another sentence, another paragraph, another quiet clue. As we drift beneath this invisible glow, something else becomes clear. The background radiation fills even the emptiest regions between galaxies. It gently warms every lonely atom. Without it, some places would become even colder than they already are. Yet astonishingly, nature has discovered a way to produce temperatures even lower than this ancient cosmic glow. Somewhere among dying stars, expanding gas performs an extraordinary trick. It cools beyond the temperature left by creation itself, beyond the oldest light, beyond the quiet memory of the Big Bang. And there, in that almost impossible place, we will discover the coldest natural region ever observed in the known universe. Imagine waking on a winter morning before anyone else. The window is covered with delicate frost. Tiny crystals spread across the glass like silent branches, each pattern formed slowly during the night. No artist touched the window. No careful hand carved those fragile lines. Nature simply allowed warmth to leave. Water molecules slowed. They settled into beautiful order. What appears lifeless is actually the beginning of structure. That quiet transformation offers one of the best ways to understand how stars are born. Most people imagine stars beginning with fire. Brilliant explosions, violent collisions, rivers of molten plasma. Yet nearly every star begins with the opposite. It begins with cold, extraordinary cold. A darkness so gentle that atoms barely move. Across the Milky Way drift immense molecular clouds. From Earth, they often appear as dark patches blocking the light of distant stars. Early astronomers thought these regions were empty holes in the sky. They seemed like cosmic absences. Modern telescopes revealed something far more remarkable. Those dark silhouettes are filled with gas and microscopic dust. They are not empty at all. They are crowded beyond imagination. A single molecular cloud may stretch for hundreds of light years. Its total mass can equal hundreds of thousands of suns. Yet despite containing so much material, it remains astonishingly diffuse. If you stood inside one, you would hardly notice anything around you. The particles are spread so widely that they almost never collide. Everything feels motionless. Everything feels suspended. Temperatures inside many of these clouds fall to only 10 Kelvin, barely 10 degrees above absolute zero. At such temperatures, hydrogen molecules drift with remarkable patience. Their motion slows. Collisions become gentle. Turbulence fades. Cold becomes an architect. Imagine trying to stack marbles on a shaking table. Every vibration sends them rolling away. Now imagine the table becoming perfectly still. Suddenly, the marbles remain where you place them. Gravity can quietly gather them together. Molecular clouds behave in much the same way. Excessive heat keeps particles moving too rapidly. Extreme cold calms them enough for gravity to begin its slow work. Gravity possesses extraordinary patience. Unlike explosions, it never rushes. It simply continues pulling, hour after hour, century after century, million after million of years. Tiny regions inside the cloud gradually become slightly denser than their surroundings. Perhaps a nearby supernova sends a gentle shockwave. Perhaps two clouds drift together. Perhaps turbulence naturally creates subtle clumps. Once a region becomes just dense enough, gravity quietly gains the advantage. The collapse begins, not with violence, with surrender. More particles gather. Density increases. Gravity strengthens. The process feeds itself. Like snow rolling downhill, each new layer encourages another. Soon, the center of the cloud becomes warmer than its surroundings. Compression converts gravitational energy into heat. Ironically, the path toward a blazing new star begins inside one of the coldest environments in the galaxy. Without cold, there would be no stars. Without silence, there would be no sunrise. This paradox appears throughout nature. Seeds wait through winter before spring arrives. Butterflies rest within quiet cocoons before taking flight. Human creativity often emerges from calm reflection rather than constant noise. The universe follows a similar rhythm. Stillness prepares brilliance. Modern observatories allow astronomers to peer inside these stellar nurseries using infrared and radio wavelengths. Visible light struggles to penetrate dense dust. Infrared light travels farther. Radio waves pass almost effortlessly. Together, they reveal hidden embryos of future stars wrapped within enormous cocoons of frozen gas. Recent observations from the James Webb Space Telescope have provided extraordinary new views of these regions. Webb has detected intricate structures inside star-forming clouds, revealing icy molecules, dense filaments, and newborn protostars previously concealed from earlier telescopes. These observations continue refining our understanding of how stars and planetary systems emerge, while largely confirming the broad picture developed over decades of research. The clouds themselves resemble enormous forests. Filaments twist through darkness. Knots gather where gravity becomes strongest. Tiny points of warmth slowly appear. Every glowing infant star begins changing its surroundings. Radiation pushes nearby gas outward. Powerful stellar winds carve cavities through the cloud. What once looked like quiet darkness gradually transforms into brilliant nebulae illuminated from within. Yet not every part of the cloud forms stars immediately. Many regions remain cold for millions of years. They wait, patiently, almost timelessly. Imagine walking through a library before sunrise. Thousands of books rest quietly upon their shelves. Every story already exists. None has begun until someone gently opens the first page. Molecular clouds feel strangely similar. Countless future stars already hide within them. Gravity simply waits for the proper moment to begin each story. The dust inside these clouds also performs another remarkable task. Tiny grains become gathering places for chemistry. Individual atoms land upon their frozen surfaces. Hydrogen meets oxygen. Carbon joins nitrogen. Molecules slowly assemble. Water ice forms delicate coatings around microscopic particles. Carbon monoxide freezes. Methanol appears. Even surprisingly complex organic molecules begin emerging through countless quiet interactions. These chemical workshops operate without urgency. Temperatures remain incredibly low. Time supplies everything else. A reaction requiring only minutes inside a laboratory may require thousands of years inside a molecular cloud. The universe does not mind waiting. It possesses abundance where humanity possesses haste. Every frozen grain quietly preserves information about cosmic history. When future stars ignite, many of these icy materials survive inside comets, asteroids, and young planets. In this way, today's molecular clouds become tomorrow's oceans, tomorrow's atmospheres, perhaps even tomorrow's living worlds. The water in your own body may once have rested upon a dust grain drifting through one of these ancient clouds before the sun itself existed. That possibility carries extraordinary tenderness. Our atoms remember cold older than Earth. Our oxygen remembers darkness older than oceans. Our carbon remembers silent clouds where no life yet stirred. Perhaps this is why, looking into the night sky often awakens an unexpected feeling of familiarity. We are not merely observing those distant regions. We are remembering them. Every heartbeat contains material that once drifted through frozen interstellar silence. Every breath carries atoms that patiently survived unimaginable journeys. The universe never hurried to create us. It simply allowed cold, gravity, chemistry, and time to cooperate. Together, slowly, quietly, almost invisibly. Yet somewhere beyond these stellar nurseries exists an even stranger place. A dying star has expelled enormous shells of gas into surrounding space. As those shells raced outward, they performed an astonishing feat. They cooled so dramatically that they became colder than the ancient glow left by the Big Bang itself. Nature, somehow, found a way to become colder than creation's oldest light, and that impossible place waits. For us next, take a slow breath, then gently blow across the back of your hand for an instant. Your skin feels cooler. Nothing magical happened. Your breath was actually warmer than the surrounding air. Yet, moving air accelerated evaporation. Tiny water molecules escaped your skin. They carried heat away. The sensation became one of cooling. It is a small trick of physics. Ordinary, familiar. You have experienced it countless times without thinking. Now imagine the same principle unfolding across a cloud, larger than our solar system. That cloud exists. It drifts nearly 5,000 light-years from Earth. Astronomers call it the Boomerang Nebula. Among all naturally known places in the universe, it remains the coldest ever observed. Its temperature falls to about 1 Kelvin, only a single degree above absolute zero. Even more astonishing, it is colder than the cosmic microwave background itself, colder than the faint afterglow left by the birth of the universe. At first, this seems impossible. How can anything become colder than the ancient radiation filling all of space? Should not that background gently warm everything until they reach the same temperature? The answer lies in expansion, not the expansion of the universe, the expansion of gas. Imagine using an aerosol can. After spraying for several seconds, the metal container begins to feel cold. The compressed gas inside rapidly expands once it escapes. During that expansion, its temperature drops. Energy spreads into a larger volume. Heat becomes more diffuse. The Boomerang Nebula performs the same process, only on a scale almost beyond imagination. Long ago, the nebula was an aging red giant star. For millions of years, it quietly fused helium and heavier elements deep within its core. Eventually, its stable life approached its conclusion. Like many stars similar to our sun, it began shedding its outer layers. This was not a violent supernova. The star did not explode. Instead, it exhaled, slowly at first, then faster, then astonishingly fast. Powerful stellar winds carried enormous quantities of gas outward at tremendous speed. The material expanded so rapidly that it cooled with extraordinary efficiency. The cooling became so intense that the surrounding gas fell below the temperature of the cosmic background. Nature briefly outran the universe itself. Imagine opening a folded paper fan. The folds spread outward. The paper occupies a larger space. Nothing has disappeared. Everything has simply become more widely distributed. Energy behaves similarly. Rapid expansion stretches it thinner. The Boomerang Nebula became a masterpiece of thermal expansion. Modern radio telescopes first revealed this remarkable property by studying molecules hidden within the expanding gas. Later observations with the Atacama Large Millimeter/Submillimeter Array, better known as ALMA, provided extraordinary detail. Sensitive instruments measured the faint radiation emerging from the nebula and confirmed its astonishingly low temperature. To astronomers, it was like discovering a patch of snow surviving inside a warm desert. The finding challenged intuition, yet the laws of physics quietly supported every measurement. Interestingly, the Boomerang Nebula does not remain equally cold forever. Closer to its central star, temperatures begin rising again. Radiation slowly reheats portions of the expanding gas. The extraordinary cold occupies only specific regions where rapid expansion continues dominating the energy balance. Nothing in nature remains frozen permanently. Everything changes. Even cold evolves when telescopes photograph the nebula in visible light. Its graceful shape resembles the outline of a butterfly or a delicate bow. Dust scatters starlight into soft blue hues. Long streamers extend into surrounding darkness. It appears fragile, almost weightless, yet appearances deceive. The structure contains enough material to reshape future generations of stars and planets. Carbon, oxygen, nitrogen, countless heavier elements forged during the star's long lifetime now drift freely into the galaxy. Death becomes generosity. The old star quietly returns its treasures to space. Perhaps someday, those atoms will become another molecular cloud, another young star, another planetary system, perhaps another living world. This endless recycling forms one of the gentlest rhythms in the cosmos. Stars are not isolated performers. They belong to an immense conversation lasting billions of years. Each generation inherits material from earlier ones. Each generation leaves gifts behind. The Boomerang Nebula therefore represents more than a cold record. It becomes a bridge, a transition between endings and beginnings. There is something deeply human within that idea. Our own lives often cool in similar ways. Moments of intense activity eventually fade into quiet reflection. Childhood becomes memory. Careers become stories. Families inherit photographs, recipes, traditions, and voices that continue long after individuals have gone. Energy changes form. Meaning continues traveling. The universe repeats this pattern with remarkable elegance. Nothing important truly vanishes. It transforms. The Boomerang Nebula also reminds us that the coldest places are not necessarily the oldest, nor the emptiest. Extreme cold can arise through process rather than location, through motion rather than stillness. The fastest expansion creates the deepest chill. This lesson appears again and again throughout astrophysics. Sometimes motion creates heat. Falling matter around black holes reaches millions of degrees. Sometimes motion creates cold. Expanding gas approaches absolute zero. Context changes everything. The same physical laws produce opposite experiences depending upon circumstance. That realization encourages humility. Nature rarely obeys simple expectations. It rewards careful observation instead. Astronomers continue searching for similar objects throughout the Milky Way. A few other nebulae display impressive cooling. Yet, none naturally observed has surpassed the Boomerang Nebula's extraordinary temperature. For now, it remains the undisputed champion of cosmic cold. Recent observations have refined our understanding of planetary nebulae and stellar evolution, but they have not replaced this remarkable record. Current scientific evidence continues supporting the Boomerang Nebula as the coldest naturally known environment in the universe. There is quiet poetry hidden within that fact. The universe's coldest known place was created by a dying star's final breath. Not by violence, not by destruction, simply by letting go, as we continue drifting outward. However, another kind of cold begins to appear. Not the cold of expanding gas, not the cold of ancient radiation, but the cold preserved upon worlds where sunlight barely arrives. Frozen landscapes where nitrogen, methane, and water become harder than stone. Planets and moons that have waited unchanged since the solar system's earliest mornings. There, beneath endless darkness, cold is no longer temporary. It becomes geography. It becomes climate. It becomes home. Imagine walking across a field just before sunrise in the middle of winter. The grass crunches softly beneath your shoes. Every blade is wrapped in delicate frost. The air feels perfectly still. Even your footsteps seem quieter than usual. You reach down and touch the frozen ground. It feels solid, permanent, as though winter has claimed every corner of the landscape. Yet only a few hours later, sunlight begins its patient work. Tiny crystals melt. Water returns. The field slowly awakens. On Earth, almost every frozen place eventually remembers the sun, far beyond Neptune. Many worlds do not. There, winter is not a season. It is a way of existence. The solar system feels comfortably warm because we spend our lives close to its center. Earth circles only one astronomical unit from the sun. Light needs about 8 minutes to reach us. Every sunrise arrives with remarkable generosity. Even cloudy days receive enough energy to sustain oceans, forests, and every living creature. Move outward. Mars receives less than half of Earth's sunlight. Jupiter receives only about 4%. Saturn falls even farther into the fading glow. By the time sunlight reaches Neptune, its brightness has diminished to roughly 1/900th of what warms your face on Earth. The sun still shines. It simply appears very far away. Stand upon Neptune. If such a thing were possible, and daylight would resemble an unusually bright twilight on Earth. Continue farther still. Beyond Neptune stretches the Kuiper Belt, a vast collection of frozen worlds, tiny planets, ancient remnants, countless icy bodies left behind from the birth of the solar system. Here, sunlight becomes less like warmth and more like memory. One of these distant worlds is Pluto. For generations, people imagined Pluto as a lonely ball of frozen rock drifting through darkness. The New Horizons mission transformed that picture forever. When the spacecraft flew past Pluto in 2015, it revealed astonishing landscapes. Mountains of water ice rose several kilometers high. Nitrogen glaciers flowed slowly across broad plains. Thin hazes floated above the surface, scattering pale blue light through an atmosphere so delicate it would seem almost non-existent to us. Pluto was not dead. It was quietly active. Its average surface temperature hovers near 44 Kelvin, about -229 degrees Celsius, cold beyond ordinary experience. At those temperatures, familiar materials behave in unfamiliar ways. Water ice becomes as hard as granite. Nitrogen freezes into solid sheets. Methane forms delicate frosts. The chemistry of the landscape changes completely. Imagine visiting a world where rocks are made from frozen water, while glaciers consist of nitrogen gas turned into ice. Everything familiar quietly exchanges roles. Yet Pluto is only one traveler among many. Nearby drifts Charon, its largest moon. Together they orbit one another like silent dance partners. Farther outward lie Makemake, Haumea, Quaoar, Sedna, following one of the longest known orbits around the Sun. Each world preserves another chapter from the solar system's childhood. They have changed remarkably little over billions of years. Cold became their greatest protector. Think of an old family photograph stored inside a cool, dry attic, because it remained untouched. Its colors survive far longer than pictures exposed to sunlight and moisture. The Kuiper Belt serves a similar purpose. Extreme cold preserves ancient materials. Volatile compounds that disappeared long ago from the inner solar system continue resting upon these distant bodies. Astronomers study them because they are time capsules, frozen archives, libraries written in ice instead of paper. Beyond the Kuiper Belt may lie the distant Oort Cloud. Unlike the relatively flat Kuiper Belt, the Oort Cloud is thought to surround the solar system like an enormous sphere. Scientists infer its existence from the paths of long-period comets. No spacecraft has visited it. No telescope has directly photographed its countless icy members. It remains a well-supported scientific hypothesis, built from orbital evidence rather than direct observation, if it exists as current models suggest. The Oort Cloud extends perhaps tens of thousands of astronomical units from the Sun. There, sunlight becomes almost meaningless. The Sun itself shrinks into a brilliant star among many others. Imagine sailing so far across the ocean that your homeland disappears into the horizon until it becomes only another distant light. That is roughly how the Sun would appear. Cold there becomes almost absolute, not because of some mysterious force, simply because warmth can no longer travel effectively across such unimaginable distance. Yet another remarkable kind of frozen landscape exists much closer to home. Even our own moon hides places where sunlight has never reached. Near the lunar poles lie deep craters. Their walls stand so high that the sun never climbs above the rim. Some of these regions have remained in permanent shadow for billions of years. Temperatures there may fall below 30 Kelvin, colder than Pluto's surface. These silent craters preserve ancient water ice delivered by comets and asteroids across immense spans of time. Mercury, surprisingly, possesses similar places. Although Mercury's sunlit side becomes hot enough to melt lead, its permanently shadowed polar craters remain among the coldest environments in the inner solar system. The contrast feels almost unbelievable. Scorching sunlight only a few kilometers away. Timeless darkness preserving ice for billions of years. Nature delights in paradox. Heat and cold often become neighbors. Brightness and shadow coexist. The universe rarely chooses simplicity. These frozen worlds also teach another quiet lesson. Distance changes perspective. On Earth, we measure journeys in kilometers. Within the solar system, we measure astronomical units. Between stars, we measure light years. Each larger scale invites greater patience. A signal from Pluto requires hours to reach Earth. A spacecraft requires nearly a decade to arrive. Time stretches alongside distance. Perhaps this explains why the outer solar system feels dreamlike. Everything happens more slowly. Sunrises last longer. Seasons endure for decades or even centuries. Pluto completes one orbit around the Sun in about 248 Earth years. No human has ever watched an entire Plutonian year unfold. Entire civilizations have risen and fallen during a single season on some distant worlds. There is unexpected peace in that rhythm. Not everything must happen quickly. Not every journey demands urgency. Some stories require centuries. Some landscapes reward only extraordinary patience. As we drift among these frozen worlds, another question quietly emerges. If cold preserves ancient materials so perfectly, what else might it protect? Perhaps tiny grains older than Earth. Perhaps untouched chemistry from the dawn of the solar system. Perhaps clues about how oceans first arrived on young planets. The answers wait inside wandering visitors, made almost entirely of ice. Silent travelers that spend millions of years drifting through darkness before briefly approaching the warmth of the sun. We know them by a simple name: comets. Imagine standing beside a frozen lake in the quiet heart of winter. Snow covers the surface. The ice seems perfectly still. From above, it appears lifeless. Yet beneath that silent shell, dark water continues moving. Tiny currents drift slowly through the darkness. Fish swim without ever seeing the winter sky. The cold above protects the liquid world below. It is a familiar scene, a peaceful contradiction. Ice can hide warmth. Silence can hide motion. The solar system contains a world built upon that very paradox. Its name is Europa. At first glance, Europa appears simple. A bright sphere wrapped almost entirely in ice. It circles Jupiter every 3.5 days, carried endlessly through the giant planet's immense gravitational embrace. From a distance, it looks calm, smooth, quiet, almost untouched. Yet appearances have deceived us before. The Moon once seemed barren. Mars once seemed completely dry. Pluto once seemed little more than a frozen rock. Again and again, careful observation has revealed deeper stories. Europa may hold one of the deepest. Its surface temperature averages only around 100 Kelvin, about minus 173 degrees Celsius. Under such conditions, water ice becomes as hard as stone. The landscape fractures into enormous plates, crossed by long reddish lines stretching thousands of kilometers. Few impact craters remain visible. Something has slowly renewed the surface over immense periods of time. Something beneath the ice has remained active. Imagine placing your hands around a small block of frozen butter. The outside feels solid. Yet, leave it near gentle warmth long enough, and the center begins changing first. Europa experiences a similar process. Although the source of heat is entirely different, the Sun contributes surprisingly little. Jupiter does. Europa follows a slightly elliptical orbit. As it circles the giant planet, Jupiter's overwhelming gravity continually squeezes and relaxes the Moon. The process resembles gently bending a paperclip back and forth. Eventually, the metal warms from repeated flexing. Europa's interior behaves in much the same way. Its rocky core experiences constant tidal flexing. That mechanical energy slowly becomes heat. Not enough to melt the surface. Enough, scientists believe, to maintain a global ocean beneath the ice. Current evidence strongly supports the existence of this hidden ocean. Multiple spacecraft observations have measured Europa's magnetic behavior, surface geology, and gravitational properties. Together, they point toward a vast layer of salty liquid water beneath the frozen crust. The ocean may contain more water than all of Earth's oceans combined. The thought feels astonishing. One of the coldest visible worlds in the solar system may hide one of its largest oceans. Recent observations continue refining this remarkable picture. The James Webb Space Telescope has detected carbon dioxide concentrated in specific regions of Europa's surface. Scientists interpret this as additional evidence that material from the subsurface ocean may occasionally reach the exterior. Although important questions remain about the exact pathways involved. Meanwhile, preparation continues for NASA's Europa Clipper mission, designed to investigate the moon's habitability in unprecedented detail. These observations strengthen scientific interest, but they do not constitute evidence that life has been found. That distinction matters. Science advances through careful patience. Observation first, interpretation second, conclusions only after sufficient evidence. The possibility of life beneath Europa's ice remains exactly that, a possibility, not a discovery. Still, possibilities can be beautiful. Imagine swimming through a dark ocean where sunlight has never entered. No blue sky, no sunrise, no moonlight dancing upon waves. Yet warm water rises from hydrothermal vents along the rocky seafloor. Minerals dissolve into the surrounding sea. Chemical reactions quietly unfold. Something similar already exists on Earth. Deep within our own oceans, life flourishes around hydrothermal vents thousands of meters below the surface. Entire ecosystems survive without sunlight. Instead, microorganisms draw energy from chemical reactions involving sulfur and other compounds. Tube worms, crabs, shrimp. Strange creatures thrive in complete darkness. Europa raises an irresistible question. Could another ocean discover similar solutions? No one knows. That uncertainty is part of the wonder. The ice above performs another important role. It shields the hidden ocean from Jupiter's intense radiation. The giant planet traps enormous numbers of energetic particles within its magnetic field. Europa's surface experiences constant bombardment. Life exposed there would face extraordinary challenges. The ice becomes more than frozen water. It becomes protection, a roof, a patient guardian. Sometimes the coldest environments preserve the greatest hope. That thought echoes through many chapters of cosmic history. Frozen molecular clouds protect delicate chemistry. Comets preserve ancient water. Polar craters safeguard ice for billions of years. Now Europa's frozen shell may protect an entire hidden ocean. Cold often appears hostile, yet again and again it becomes a caretaker. Imagine placing precious photographs inside a cool archive. Temperature slows decay. Time itself seems to soften. Museums carefully control climate because preservation depends upon stability. The solar system possesses its own archives. Europa may be among the most extraordinary. Its surface also tells stories through fractures. Long ridges weave across the landscape like cracks in old porcelain. Some regions resemble broken sea ice drifting upon Earth's polar oceans. Scientists believe portions of the crust may slowly shift, rotate, and refreeze over immense spans of time. The moon breathes, not with air, with ice. Every fracture becomes another sentence in a geological diary. Every ridge records another cycle of stress and release. Watching these patterns from orbit feels strangely calming. They remind us that movement. Picture a frozen lake at the end of winter. The surface appears perfectly still. Snow covers every familiar feature. Beneath your feet lies a thick sheet of ice that seems solid enough to last forever. Yet somewhere below that silent surface, dark water continues moving. Gentle currents drift through unseen depths. Tiny fish navigate a world hidden from the sky. To someone standing above, the lake appears asleep. In truth, it has never stopped living. This simple scene offers one of the best ways to imagine Europa. From a distance, Europa looks quiet, bright, smooth, almost fragile. It circles Jupiter every 3.5 days, wrapped inside one of the coldest environments in the inner reaches of the outer solar system. Sunlight there is only a faint fraction of what reaches Earth. The surface temperature often falls near 100 Kelvin, around -173 degrees Celsius. To human senses, it would feel unimaginably cold, yet that frozen surface may hide one of the most intriguing places in our solar system. Europa is slightly smaller than Earth's moon. At first glance, it resembles a polished sphere of pale ice crossed by long reddish cracks. Unlike heavily cratered worlds, Europa has surprisingly few impact scars. Its surface appears young. Something has been renewing it over immense spans of time. Scientists believe the answer lies beneath the ice. Most current models indicate that a global ocean of liquid water likely exists below Europa's frozen crust. That ocean may contain more water than all of Earth's oceans combined. It does not remain liquid because of sunlight. Sunlight is far too weak. Instead, Jupiter performs the heating. Europa follows a slightly elliptical orbit. As it circles the giant planet, Jupiter's enormous gravity gently stretches and squeezes the moon over and over again. The process resembles repeatedly bending a metal paperclip. Bend it enough times and it becomes warm in your fingers. Europa experiences a similar effect on a planetary scale. This process is called tidal heating. Gravity becomes friction. Friction becomes warmth. Warmth prevents the deep ocean from freezing solid. Imagine slowly kneading a ball of dough. Your hands continuously compress and release it. Tiny movements create heat. Europa undergoes this quiet kneading every orbit. The movement is incredibly small, yet across an entire moon, repeated billions of times, it becomes sufficient to maintain liquid water beneath kilometers of ice. This hidden ocean has fascinated scientists for decades. Where liquid water exists, curiosity naturally follows. On Earth, life appears almost everywhere water remains liquid, deep beneath Antarctic ice, around hydrothermal vents at the bottom of the oceans, inside underground caves untouched by sunlight. Microorganisms repeatedly demonstrate that life can adapt to environments once thought impossible. Europa therefore represents possibility, not proof. Possibility. This distinction matters. Modern science has found no verified evidence that life exists on Europa. None. Every responsible mission, observation, and scientific paper carefully separates hope from evidence. The moon offers conditions that may be favorable. Whether life actually emerged remains unknown. That uncertainty makes Europa even more compelling. Questions often endure longer than answers. Recent observations using the James Webb Space Telescope and other facilities have strengthened our understanding of Europa's surface chemistry. Researchers continue studying carbon dioxide, salts, and the complex interactions between the icy crust and the hidden ocean beneath. These observations suggest that material from the ocean may sometimes reach the surface through fractures or other geological processes. They improve our understanding of Europa's environment. They do not confirm biology. The ice itself tells a remarkable story. Across Europa stretch immense fractures that weave around the moon like veins across marble. Some extend for thousands of kilometers. Others intersect in chaotic patterns where large blocks appear to have shifted, rotated, and frozen again. Imagine a frozen pond during early spring. The ice begins cracking. Large sheets slowly separate. Water briefly rises. Then another freeze locks everything into a new arrangement. Europa may have experienced similar events over millions of years. Although on a vastly greater scale, some regions resemble shattered mosaics. Scientists call them chaotic terrain, and these landscapes hint that warm material occasionally approaches the surface from below before cooling once again. The moon becomes a conversation between heat and cold. Neither side fully wins. The surface belongs to winter. The depths quietly remember warmth. Soon humanity will examine Europa more closely than ever before. NASA's Europa Clipper mission is designed to perform dozens of close flybys after arriving in the Jovian system. Rather than landing immediately, the spacecraft will repeatedly sweep past the Moon, measuring the thickness of the ice, mapping surface chemistry, studying magnetic fields, and searching for evidence that the hidden ocean communicates with the surface. Each pass will reveal another piece of an enormous puzzle. The mission carries remarkable patience. No dramatic promises, no declarations of discovery before the evidence exists. Only careful observation, one measurement at a time. This is how science usually advances. Quietly, methodically, with curiosity stronger than certainty. Europa also changes how we think about warmth itself. For most of human history, we assumed sunlight determined where life could exist. The farther from the sun, the less hopeful a world appeared. Europa gently challenges that assumption. Internal energy may sometimes matter more than external light. Gravity can replace sunshine. Hidden oceans can survive beneath frozen shells. Warmth does not always arrive from above. Sometimes it rises from within. That idea reaches beyond astronomy. Many of life's most meaningful changes begin invisibly. A person's confidence often grows quietly before others notice. Forgiveness forms long before words are spoken. Hope frequently survives beneath surfaces that appear completely frozen. Perhaps that is why Europa feels strangely familiar, despite its impossible distance. Its greatest mystery is concealed beneath silence. As we drift away from Jupiter, the Moon slowly fades into darkness once again. Its bright ice reflects the distant sun like polished ivory against black velvet. Beneath that frozen shell, if current understanding is correct, an unseen ocean continues its endless motion. No waves reach the sky, no winds disturb the surface. Only darkness, only ice, only patient possibility. Yet even Europa cannot preserve the oldest materials in the solar system forever. For that, we must follow travelers that spend millions of years beyond the warmth of the planets, wanderers that sleep in profound cold until gravity gently calls them inward. They arrive trailing delicate streams of dust and ice, carrying untouched memories from the dawn of our cosmic neighborhood. They are the oldest frozen messengers we have ever known, comets. Imagine finding an old wooden chest hidden inside the attic of a quiet farmhouse. Dust covers the lid. The hinges creak softly as you lift it open. Inside rest letters written generations ago. The paper has yellowed. The ink has faded. Yet the words remain. Time touched everything, except the story itself. Cold often works this way. It becomes a careful librarian. It slows change. It protects memory. The solar system possesses countless such libraries. They drift silently beyond the planets. They spend millions, sometimes billions, of years in darkness. We call them comets. To many people, a comet is simply a bright object decorating the night sky with a glowing tail. It arrives unexpectedly. It dazzles for a few weeks. Then it disappears once again. Beautiful, temporary, almost magical. Yet the glowing tail is only the final chapter. The real story begins much farther away. Long before a comet develops its brilliant appearance, it sleeps in extraordinary cold. Many originate in the Kuiper Belt. Others likely come from the distant Oort Cloud, a vast spherical reservoir inferred from the orbits of long-period comets. These regions receive so little sunlight that temperatures remain only a few tens of degrees above absolute zero for immense stretches of time. Nothing seems to happen. A comet drifts. It waits. Gravity patiently guides its orbit. Millions of years pass like quiet breaths. Imagine placing a loaf of bread inside a freezer. Months later, it changes very little compared with bread left upon a kitchen table. Low temperatures slow almost every chemical process. Nature becomes an excellent preserver. Comets experience that preservation for billions of years. Many scientists regard them as frozen relics from the earliest days of the solar system. They formed when the sun was still surrounded by a vast disk of gas and dust. Planets gradually assembled. Countless smaller bodies remained behind. Some became asteroids. Others formed icy nuclei rich in frozen water. Carbon dioxide, methane, ammonia, and many other compounds. These tiny worlds became cosmic archives. Each one quietly stored information about conditions that existed before Earth possessed oceans, before mountains rose, before life began. Eventually, gravity nudges one of these ancient travelers inward. Perhaps a passing star slightly disturbs the distant Oort Cloud. Perhaps interactions among giant planets slowly reshape an orbit. Whatever the cause, the comet begins falling toward the sun. At first, almost nothing changes. Sunlight grows gradually brighter. Temperatures increase slowly. Then an invisible threshold arrives. The frozen surface begins awakening. Ice no longer remains solid. Instead of melting into liquid water, many frozen materials pass directly into gas through a process called sublimation. Dry ice behaves similarly on Earth. It transforms from solid carbon dioxide directly into vapor without becoming liquid. A comet breathes. Gentle jets of gas erupt through tiny cracks. Dust trapped inside the ice escapes alongside the vapor. The nucleus, often only a few kilometers across, suddenly surrounds itself with an enormous cloud called the coma. The coma may become larger than an entire planet. Sunlight strikes this expanding cloud. Radiation pressure and the solar wind gently push material away. The familiar tail appears. Ironically, the magnificent tail people admire is not what preserves history. It is what history releases. Every glowing streamer represents ancient material returning to space after remaining frozen for billions of years. In this sense, every comet tells two stories simultaneously, one about preservation, one about transformation. Recent observations have expanded this story even further. The James Webb Space Telescope has examined several comets in remarkable detail, measuring the distribution of water vapor, carbon-bearing molecules, and other volatile compounds with unprecedented sensitivity. Webb has also observed interstellar objects and distant icy bodies, helping astronomers compare material formed within our solar system to visitors originating around other stars. These observations continue refining our understanding of planetary formation while reinforcing the idea that comets preserve extraordinarily ancient chemistry. Yet caution remains essential. Finding organic molecules does not mean finding life. Organic chemistry is common throughout the universe. Biology is something different. Scientists carefully distinguish between the building blocks of life and life itself. This careful language protects truth. It also preserves wonder. Because reality rarely needs exaggeration, one fascinating possibility continues attracting attention. Many researchers believe comets may have delivered significant amounts of water and complex molecules to the young Earth during the solar system's early history. Exactly how much remains an active area of research. Different comets possess different chemical fingerprints. Some match Earth's oceans more closely than others. Asteroids likely contributed as well. The picture continues evolving. Science rarely offers a single dramatic answer. Instead, it assembles countless small pieces, like restoring an ancient mosaic, one tile at a time. Imagine rain falling upon a dry garden after years of drought. Each drop seems insignificant. Together, they awaken the landscape. The early Earth may have experienced something similar, not from ordinary rain, but from countless icy visitors arriving over immense spans of time. Every impact delivered another small gift, another handful of water, another collection of carbon compounds, another opportunity. Whether comets played a major role or a supporting one, they unquestionably carried ancient ingredients across the young solar system. Their journeys connected distant frozen regions with newly forming worlds. Perhaps that is their greatest lesson. Distance does not prevent generosity. Something preserved in darkness can eventually nourish light. There is quiet comfort in that thought. Human memories often behave similarly. Experiences long forgotten suddenly return when a familiar song begins playing. A scent recalls childhood. An old photograph awakens forgotten voices. Nothing truly disappeared. It merely waited. Cold teaches patience. Comets teach timing. For billions of years, they remain almost invisible. Then, for a few brief weeks, they become among the most beautiful objects in the sky. Their brilliance depends entirely upon their long years of silence. As each comet departs once again, sunlight weakens. The coma slowly fades. The tail disappears. The nucleus cools. Darkness welcomes it home. It resumes its patient orbit, waiting for another distant future encounter. Watching these travelers reminds us that the universe values endurance as much as spectacle. Most of a comet's existence unfolds far from attention. Only a tiny fraction becomes visible to observers on Earth. Yet, without those long hidden years, there would be no luminous display. Perhaps our own lives resemble that pattern more than we realize. Growth often occurs quietly. Preparation happens unseen. The brightest moments rest upon foundations built in silence. Still, comets carry only part of the story. Before these frozen messengers ever formed, countless microscopic grains drifting through interstellar clouds were already building remarkable molecules upon their icy surfaces. In darkness, colder than almost anything we have yet explored, chemistry patiently assembled the ingredients that would someday become planets, oceans, and perhaps living worlds. The smallest frozen objects may have prepared the greatest possibilities. Imagine opening the freezer late at night. The kitchen is quiet. A small light fills the shelves with a gentle glow. Ice crystals cover forgotten containers. Frost gathers around the edges of old packages. Time seems slower inside this little chamber. Food that would spoil within days on the countertop remains unchanged for months. Cold does not stop chemistry completely. It simply asks chemistry to be patient. Across the Milky Way, nature has built freezers far larger than imagination. No electricity powers them. No doors protect them. Only darkness. Only silence. Only temperatures barely above absolute zero. Inside these immense frozen regions drift microscopic grains of dust. Each grain is astonishingly small. Many measure less than a single micrometer across. If one rested upon your fingertip, thousands could fit beneath the width of a human hair. Tiny, almost invisible, yet these grains quietly shape the future of planets. At first, they appear unremarkable. Small particles made from silicates, carbon-rich material, and traces of heavier elements forged inside ancient stars. But as they drift through molecular clouds colder than 10 Kelvin, something extraordinary begins. Atoms land upon their surfaces, one after another. Hydrogen arrives, then oxygen, carbon, nitrogen. Simple ingredients gently gather. Imagine children placing tiny bricks onto a frozen pond. No one rushes. Every new brick waits quietly for the next. Eventually, a small structure appears. The dust grains perform a similar role. Their icy surfaces allow atoms to remain together long enough for chemical reactions that would otherwise happen only rarely. Water begins forming. Hydrogen meets oxygen. Thin layers of ice slowly coat each grain. Carbon monoxide freezes beside it. Methanol appears. Ammonia joins the growing collection. Even more complex organic molecules quietly emerge through countless patient interactions. No explosions, no dramatic flashes, only millions of years. The laboratory works without interruption. Cold becomes the chemist. Scientists have long suspected that many important molecules formed this way before planets even existed. Recent observations have strengthened that idea. Powerful instruments aboard the James Webb Space Telescope have detected abundant water ice, carbon dioxide ice, methane ice, and other frozen compounds within star-forming regions. These observations allow astronomers to study the chemistry of stellar nurseries with remarkable precision, rather than beginning on warm young planets. Parts of life's chemical story may begin inside frozen clouds, drifting between the stars. Again, careful language matters. These molecules are not life. They are ingredients. The difference is profound. Flour is not bread. Seeds are not forests, yet without ingredients. Later, creations become impossible. Another recent mission has begun expanding this picture even further. NASA's Spherix Observatory is mapping enormous regions of the sky in infrared wavelengths, helping astronomers identify vast reservoirs of interstellar ice and trace where different frozen compounds gather across our galaxy. As observations continue, researchers hope to understand how chemistry changes from one molecular cloud to another, and how those differences influence the birth of planetary systems. Each new observation adds another sentence. Never the entire story, always another page. Imagine snowfall covering an empty field. Every individual snowflake seems insignificant. Together, they transform the entire landscape. Molecules accumulate upon dust grains in much the same way. One atom changes almost nothing. Billions upon billions gradually reshape entire clouds. Eventually, gravity begins pulling portions of those clouds inward. Amid the collapse that creates new stars also gathers these icy grains. They spiral around newborn suns inside enormous rotating disks. Astronomers call them protoplanetary disks. Within these graceful structures, dust slowly collides. Tiny grains become pebbles, pebbles become rocks. Rocks become mountain-sized bodies. Planets quietly emerge. Remarkably, much of the ancient ice survives the journey. Some becomes trapped inside comets. Some enters asteroids. Some eventually reaches young planets. The water filling Earth's oceans may have begun as microscopic frost, coating dust grains long before the sun itself ignited. That possibility carries astonishing emotional weight. The glass of water resting beside your bed tonight may contain molecules assembled inside a frozen cloud older than our solar system. The oxygen passing through your lungs may remember darkness that existed before Earth possessed a sky. Memory travels farther than we imagine, not through thought, through atoms. The chemistry inside these frozen clouds also teaches humility. Human beings often associate creativity with speed, quick decisions, rapid innovation, instant results. Nature prefers another rhythm. Its greatest constructions often require extraordinary patience. Stars spend millions of years preparing to ignite. Planets require tens of millions more. Complex chemistry quietly unfolds over immense timescales. Nothing hurries. Nothing complains. Everything simply continues. There is comfort hidden inside that pace. Modern life often celebrates urgency. Notifications arrive constantly. Clocks measure every minute. Schedules fill every hour. The universe whispers a different lesson. Important things sometimes happen almost invisibly. The oak tree grows while no one watches. Glaciers reshape mountains one silent season after another. Interstellar chemistry patiently prepares future oceans across spans longer than human civilization itself. Perhaps our own lives benefit from remembering that slower rhythm. Not every meaningful change requires immediate results. Some transformations need quiet, need stillness, need time. Astronomers continue searching these frozen clouds using infrared observatories because visible light cannot easily penetrate thick dust. Infrared wavelengths slip between the particles, revealing hidden reservoirs of ice and the faint signatures of individual molecules. Every spectrum becomes a fingerprint. Every fingerprint reveals another ingredient quietly waiting inside the darkness. The remarkable discovery is not simply that these molecules exist. It is where they exist. They form under conditions once thought too cold for interesting chemistry, instead of preventing complexity. Extreme cold often preserves delicate reactions long enough for complexity to emerge. The universe repeatedly overturns our expectations. Warmth creates motion. Cold creates memory. Heat drives transformation. Cold preserves possibility. Both become necessary. Both belong to the same story. As newborn stars ignite within these ancient clouds, much of the surrounding material begins changing once again. Radiation grows stronger. Planetary systems slowly organize themselves. Some icy bodies remain nearby. Others are scattered toward distant reservoirs like the Kuiper Belt and Oort Cloud. Still others plunge inward, carrying frozen chemistry toward young terrestrial planets. The journey continues. Nothing truly ends. Everything becomes another beginning. Yet there are travelers that have carried humanity's own creations farther into this frozen darkness than any natural comet we have followed closely. Small machines, built by human hands, now drift through regions where sunlight has become astonishingly faint. They continue speaking softly across billions of kilometers, crossing one of the coldest frontiers our civilization has ever reached. Their names are Voyager. Imagine leaving your home on a winter evening. The porch light remains behind you. Each step down the quiet road makes that warm circle of light appear smaller. After a few minutes, it becomes only a distant glow. Continue walking long enough, and the house itself disappears into the darkness. Nothing happened to the house. Nothing happened to the light. Only distance changed your experience. The Voyager spacecraft have spent nearly half a century repeating this quiet journey. Every year they travel farther from the sun. Every year sunlight becomes weaker. Every year, Earth becomes harder to imagine from where they drift. When Voyager 1 launched in September 1977, engineers expected a mission lasting only a few years. Voyager 2 followed a few weeks later. Both spacecraft were built to visit the giant planets during a rare planetary alignment that would not occur again for generations. No one imagined they would become humanity's longest travelers. Today they continue moving through interstellar space, not toward any particular star, simply onward, patiently, silently, carried by momentum. Imagine throwing a small paper boat into a slow river. Long after you have forgotten it, the boat continues floating downstream. The Voyagers resemble those paper boats, except their river is gravity itself, and their journey spans billions of kilometers. As they departed the inner solar system, they transformed our understanding of the giant planets. Voyager 1 revealed astonishing details of Jupiter and Saturn. Voyager 2 continued farther, becoming the only spacecraft ever to visit Uranus and Neptune. Those encounters lasted only days. The journey afterward has lasted decades. Eventually, both spacecraft crossed the heliosphere. The heliosphere is often described as a vast bubble created by the solar wind. Charged particles flowing outward from the sun gradually push against the thin gas between the stars. This invisible boundary surrounds our planetary system like a protective cocoon. Beyond it lies interstellar space, not completely empty, not completely still, just different. When Voyager 1 crossed the heliopause in 2012 and Voyager 2 followed in 2018, humanity entered interstellar space for the first time through machines of its own making. Neither spacecraft left the solar system entirely. That much larger journey will require tens of thousands of years. But they did leave the sun's protective wind behind. The change was subtle, not dramatic. Particle densities shifted. Magnetic fields behaved differently. The temperature of the surrounding plasma increased. Although the gas remained so incredibly thin that almost no heat could actually transfer to the spacecraft. This distinction surprises many people. Scientists sometimes describe interstellar plasma as having temperatures of thousands of degrees. Yet the density is extraordinarily low. There are so few particles that almost none collide with the spacecraft. Heat depends not only upon temperature, but also upon how much material exists to exchange energy. Imagine placing your hand near a glowing ember. Now imagine placing it inside a room containing only a handful of glowing sparks floating far apart. The sparks may each be extremely hot. Your hand barely notices them. Interstellar space behaves similarly. The measured particle temperatures sound astonishing. the practical environment remains profoundly cold. The Voyagers themselves slowly lose warmth, not because something steals it violently, simply because they continue radiating energy into the surrounding darkness. Each spacecraft carries radioisotope thermoelectric generators. Inside them, plutonium slowly decays. The released heat becomes electricity. Electricity powers instruments, transmitters, computers, tiny heaters protecting sensitive components. Year after year, radioactive decay naturally decreases. The available electrical power slowly falls. Mission engineers make difficult decisions. One instrument is turned off, later another, then another. Each shutdown conserves enough energy for the remaining systems to survive a little longer. The process feels strangely gentle, not failure, conservation. Imagine an old lighthouse after the nearby town has disappeared. Its keeper carefully extinguishes unnecessary lamps one by one so that the main beacon may continue shining through one more winter. The Voyager team has practiced this quiet wisdom for decades. Every watt matters, every degree matters, every remaining signal matters. Despite traveling more than 20 billion kilometers from Earth, Voyager 1 still whispers home. Its radio signal moves at the speed of light, yet requires well over 20 hours to reach us. A reply from Earth requires another 20 hours. A simple conversation spans nearly 2 days. Patience becomes unavoidable. The Deep Space Network receives these astonishingly faint transmissions using enormous radio antennas positioned around the world. By the time Voyager's signal reaches Earth, its power is comparable to detecting the energy of a refrigerator light bulb from across the width of the United States. Yet we still hear it, softly, faithfully. There is quiet beauty in that accomplishment. A small machine built in the 1970s continues speaking across interstellar darkness, using technology older than many people alive today. It reminds us that endurance often matters more than perfection. The spacecraft also carries something deeply symbolic. Each contains a golden record, a gold-plated copper disc filled with sounds and images representing life on Earth. Greetings spoken in many languages, music from different cultures, natural sounds of wind, rain, birds, and waves. The record was never intended as a likely message. The probability of another civilization finding it remains extraordinarily small. Instead, it serves another purpose. It reflects humanity back to itself. Imagine placing a letter inside a bottle and releasing it into the ocean. Fully aware that no one may ever discover it, you still write carefully. Not because discovery is guaranteed, because the act itself carries meaning. The golden record is that bottle. It drifts through one of the coldest frontiers we have ever reached, carrying laughter, music, hope, memory. Eventually the spacecraft will fall silent, not because they reached the end of space, simply because their remaining power will no longer support communication. They will continue traveling, dark, cold, wordless, for millions of years, long after continents on Earth have shifted, long after today's cities have become geology. The Voyagers will still drift between the stars, tiny ambassadors carried by inertia alone. Watching them disappear into darkness teaches a surprisingly comforting lesson. Not every journey requires arrival. Some journeys exist simply to continue. Some questions remain open. Some stories never truly finish. Yet even the Voyagers travel through a universe that continues cooling. Every billion years, the great cosmic background grows slightly colder. Every trillion years, more stars complete their lives. Eventually, even the brightest galaxies will fade. The deepest cold does not belong only to distant places. It belongs to the future itself. Imagine watching the final ember in a fireplace after everyone else has gone to bed. Hours earlier, bright flames danced across the wood. Warm light filled the room. Shadows flickered gently upon the walls. Conversation felt effortless beside the comforting heat. Now, only a faint orange glow remains. One small ember quietly releases the last of its stored warmth. Eventually, even that glow fades. The fireplace does not suddenly become cold. It simply continues a journey that began the moment the first flame appeared. The universe is following a similar path, not tonight, not tomorrow, not even during the lifetime of our sun, but across stretches of time so immense that ordinary numbers lose their meaning. Human history measures thousands of years. Recorded civilization spans only a few thousand more. The dinosaurs ruled Earth for roughly 160 million years. The universe has existed for nearly 13.8 billion years. Yet even that astonishing age represents only the opening pages of its story. Stars continue shining because they contain concentrated stores of energy deep inside their cores. Gravity compresses hydrogen until nuclear fusion begins. Tiny amounts of mass become tremendous amounts of light. Every sunrise on Earth exists because this process has continued without interruption and for billions of years. But every fire has fuel. Every candle eventually shortens. Every star slowly changes. Our sun still possesses enough hydrogen to shine for about another 5 billion years. To human minds, that seems almost eternal. Yet compared with the lifetime of the universe itself, it is simply another chapter. Imagine an hourglass so enormous that a single grain of sand falls every 1,000 years. Watching it would feel impossible. Yet eventually, every grain would reach the bottom. Stars experience similar patience. The smallest red dwarfs burn their fuel extraordinarily slowly. Some may continue shining for trillions of years. They consume hydrogen with remarkable efficiency. Gentle, steady, almost timeless. Massive stars live differently. They burn brilliantly, rapidly. Their lives resemble fireworks rather than candles. Within only millions of years, they exhaust their fuel and die in spectacular explosions. Different stars choose different rhythms. The ending remains the same. Eventually, fusion stops, without continuous nuclear reactions replacing lost energy. Stars begin cooling. White dwarfs offer a beautiful example. After sun-like stars shed their outer layers, the remaining cores continue glowing from stored heat. No new fusion occurs. They simply radiate away ancient warmth. Imagine removing a loaf of bread from the oven. It remains hot long after baking ends. No new heat is created. The bread merely releases energy accumulated earlier. White dwarfs behave the same way, only instead of cooling over hours, they cool across billions and eventually trillions of years. Astronomers have never observed a true black dwarf, not because the theory is uncertain, because the universe is not old enough. A black dwarf represents a white dwarf that has cooled almost completely, becoming dark and nearly invisible. Calculations suggest this transformation requires far longer than the present age of the cosmos. Some futures remain impossible, simply because time itself has not yet traveled that far. This thought feels strangely comforting. The universe still possesses unfinished dreams. Neutron stars cool as well. These astonishing objects contain more mass than the sun compressed into a sphere only about 20 kilometers across. Immediately after formation, they blaze with extraordinary heat. Over millions of years, they gradually lose thermal energy. Their surfaces become cooler. Although powerful magnetic fields and occasional interactions with surrounding matter may briefly restore energetic activity, even the densest stars cannot escape the patient flow of entropy. Black holes introduce another remarkable chapter. For generations, scientists imagined black holes as eternal prisons from which nothing could ever escape. Modern physics presents a subtler picture. According to Stephen Hawking's theoretical work, quantum effects near the event horizon allow black holes to emit an incredibly faint form of radiation, Hawking radiation. For stellar black holes, this radiation is unimaginably weak. They absorb far more energy from the universe than they emit, only after incomprehensibly long periods. Once the surrounding universe has cooled dramatically, would evaporation slowly dominate? The process unfolds across timescales almost impossible to describe. Not billions, not trillions, far longer. Again, observation has not yet confirmed Hawking radiation directly, It remains one of the most influential theoretical predictions in modern physics, supported by mathematical reasoning, but still awaiting direct experimental verification. Science carefully distinguishes theory from observation. Both matter. They simply occupy different places upon the path toward understanding. As stars gradually disappear, galaxies themselves begin changing. New star formation slows. Existing stars grow older. Bright blue giants become rare. Long-lived red dwarfs quietly dominate the remaining light. Night becomes darker, not suddenly, patiently. Imagine a great city where one window after another quietly turns off its lamp. At first, the streets remain bright. Hours later, only scattered lights remain. Dawn has not arrived. The city has simply gone to sleep. The future universe may resemble that sleeping city. Light persists, just less frequently. Cosmologists sometimes speak of the stelliferous era, the age when stars dominate the cosmos. Humanity lives comfortably within it. We inhabit one of the brightest periods the universe will ever know. That realization changes perspective. We often think we arrived late. Instead, cosmically speaking, we arrived remarkably early. We live while galaxies still sparkle, while planets still form, while warmth still gathers around countless suns. This age will not last forever. Nothing does. Yet its temporary nature makes it precious. There is another quiet lesson hidden here. Cold is not the enemy of warmth. Cold gives warmth meaning. Without winter, spring loses part of its beauty. Without night, sunrise becomes ordinary. Without silence, music cannot breathe. The universe teaches this balance repeatedly. Every blazing star shines against darkness. Every memorandum plan drifts through cold. Every heartbeat unfolds between moments of stillness. Perhaps existence itself depends upon contrast. As we imagine this immense future, another question naturally appears. If stars continue fading, if white dwarfs cool, if galaxies slowly darken, what remains at the very end? What does the universe become after almost every source of warmth has surrendered its final light? The answer carries one of the quietest names in cosmology: heat death. Not an explosion, not a catastrophe, simply the longest sunset imaginable. Imagine walking through a quiet city long after midnight. Every shop has closed. Streetlights remain, but many apartment windows have already gone dark. A bakery that filled the morning with warmth now rests in silence. A cafe that echoed with conversation only hours before has stacked its chairs upon empty tables. Nothing terrible happened. The day simply ended. Activity slowly gave way to stillness. Cosmologists imagine a future that resembles this gentle transition. They call it the heat death of the universe. The name sounds dramatic. The reality is remarkably quiet. Heat death does not describe a sudden disaster. It does not involve every star exploding at once. It is not a cosmic apocalypse racing across space. Instead, it describes a state in which energy has become so evenly distributed that almost no useful work remains possible. To understand this, return once more to the familiar cup of coffee. When the coffee is much hotter than the room, something interesting can happen. Steam rises, heat flows, energy moves. There is contrast. Several hours later, the coffee and the room reach the same temperature. Nothing dramatic follows. No more steam, no more visible change. Energy still exists. It simply no longer flows in meaningful ways. The future universe may eventually resemble that quiet room. Every difference softened. Every sharp contrast faded. Entropy quietly completed its patient work. Imagine a river flowing down a mountain. As long as the water remains higher than the valley, it can turn water wheels. It can carve stone. It can generate electricity. Now imagine the river reaching the sea. The water still exists, yet the height difference has disappeared. The opportunity for work fades. The universe depends upon differences in much the same way. Stars shine because their cores are far hotter than surrounding space. Planets experience weather because sunlight creates temperature differences. Living organisms survive because chemical gradients constantly move energy through cells. Remove those differences, activity gradually slows. Life, as we understand it, becomes increasingly difficult. The phrase heat death therefore means something surprisingly gentle, not the disappearance of energy, the disappearance of useful imbalance. According to our current understanding, if cosmic expansion continues indefinitely and no unexpected new physics changes the picture, the universe will slowly approach this condition across incomprehensibly long time scales. Current observations indicate that cosmic expansion is accelerating, driven by what scientists presently describe as dark energy. Exactly what dark energy is remains unknown. We observe its effects with considerable confidence. Its underlying nature continues to be one of modern cosmology's greatest unanswered questions. This uncertainty matters. Science does not pretend to know everything. It carefully distinguishes observation from explanation. We know expansion accelerates. We do not yet fully understand why. If this expansion continues forever, distant galaxies will gradually disappear beyond our observable horizon. Not because they cease existing, because space between us expands faster than their light can eventually bridge. Imagine placing tiny boats upon a river whose current steadily increases. Each boat continues floating, yet the widening distance eventually prevents voices from carrying between them. The boats still exist. Communication quietly fades, billions upon billions of years from now. Astronomers living within the Milky Way's distant descendants might observe a remarkably different sky. Many galaxies visible today could already have vanished beyond observation. Their ancient light would no longer arrive. The universe would appear smaller, not because it became smaller, because visibility changed. This possibility carries unexpected sadness, not the sadness of destruction, the sadness of separation. Memories sometimes feel similar. People remain alive somewhere in the world. Old homes continue standing. Childhood streets still exist, yet distance quietly places them beyond daily experience. Expansion creates another form of distance. Even then, the universe would not become completely empty. Long-lived red dwarf stars would continue shining for astonishing lengths of time. White dwarfs would continue cooling. Neutron stars would quietly age. Black holes would patiently persist. The process remains gradual, always gradual. Patience once again becomes the defining language of the cosmos. Some theoretical models extend even farther. Eventually, black holes themselves may slowly evaporate through Hawking radiation. The largest require unimaginable stretches of time. Numbers become almost meaningless. Writing them requires more zeros than ordinary language comfortably accepts. These immense durations remind us that the universe thinks differently from humanity. We celebrate birthdays. The cosmos counts epochs. We watch seasons. The cosmos watches galaxies. Yet despite these differences, the same physical laws govern both. The coffee cooling beside your chair, the ember fading inside a fireplace, the white dwarf releasing ancient heat, the galaxy exhausting its gas. Each tells the same story. Energy spreads. Contrasts soften. Time continues. There is remarkable unity in that simplicity. Some people find the idea of heat death unsettling. Others find it strangely peaceful. Perhaps because it contains no anger, no punishment, no violence, only completion, like the final page of a well-loved book gently closing, or snowfall slowly covering a quiet field. Nothing resists. Everything settles. Of course, cosmology continues evolving. Alternative ideas occasionally appear. Some models explore cyclic universes. Others investigate modifications to dark energy or quantum gravity. These remain active areas of theoretical research rather than established descriptions of reality. Current observational evidence most strongly supports continued cosmic expansion, but science remains open to future discoveries should evidence require revision. This openness is one of science's greatest strengths. Confidence where evidence exists, humility where it does not. As listeners beneath today's stars, We occupy an extraordinary moment. We can contemplate futures trillions upon trillions of years away while resting comfortably upon a small planet, orbiting an ordinary star. That ability itself feels miraculous. Our species emerged from chemistry. Chemistry emerged from stars. Stars emerged from cold molecular clouds. Those clouds emerged from an expanding universe. The story circles gently back toward its beginning. Cold has accompanied every chapter, not merely as absence, as possibility, as preservation, as patience, as the quiet space where tomorrow slowly prepares itself. Perhaps that is the deepest lesson hidden within the coldest places in existence. Stillness is rarely empty. Silence is rarely meaningless. Even the darkest regions quietly carry memory, yet before we leave this journey, there remains one final destination. Not another distant nebula. Not another frozen moon. Instead, we return to ourselves, to the small warm planet where every human story has unfolded beneath a sky filled with ancient cold. Only then can we truly understand what the universe has been whispering all along. Imagine returning home after a long walk on a winter night. Your hands are cold. Your face tingles from the quiet air. You open the front door. A gentle wave of warmth greets you. The room has not become especially hot. It simply feels welcoming because you have come from the cold. A familiar chair waits by the window. A lamp casts a soft circle of light across the floor. Somewhere a kettle begins to whisper. Nothing extraordinary has happened. Yet, everything suddenly feels precious. Perhaps that is what the universe has been teaching us all along. Tonight, we have wandered across frozen molecular clouds where stars quietly prepare for birth. We have drifted through the immense darkness between galaxies, where lonely atoms travel for millions of years without meeting another. We have stood beside the Boomerang Nebula, where expanding gas became colder than the ancient glow left by creation itself. We have crossed the silent plains of Pluto, followed ancient comets, carrying untouched memories from the dawn of the solar system, and listened to the patient voices of the Voyager spacecraft as they continue their endless journey into interstellar space. Every destination shared one companion, cold, not dramatic, not angry, simply present. At first, we may think of cold as emptiness, a lack, the absence of comfort. Yet the deeper we traveled, the more that idea quietly changed. Cold preserved water before oceans existed. Cold protected delicate molecules before planets formed. Cold allowed gravity to gather sleeping clouds into newborn stars. Cold sheltered hidden oceans beneath thick sheets of ice. Cold became an archive where time itself seemed to move more gently. The universe never treated cold as an enemy. It treated it as memory. Imagine visiting an old library where every shelf holds books hundreds of years old. The air remains cool. The windows admit only gentle light. Everything has been carefully arranged to protect fragile pages from the passing years. Preservation often requires calm rather than excitement. The cosmos built its own library. Its shelves are made from darkness. Its pages are written in frozen atoms. Its stories drift quietly between the stars. We sometimes imagine humanity standing apart from this immense universe. We speak of looking outward, as though we occupy one place while the cosmos occupies another. Yet every atom within your body has already participated in this story. The calcium inside your bones formed within ancient stars. The oxygen you breathe was forged long before Earth existed. The hydrogen inside every drop of water still remembers the first few minutes after the Big Bang. Even the iron flowing through your blood once rested inside the heart of a dying star. Your body is not separate from cosmic history. It is one of its newest chapters. That realization changes something subtle. The night sky no longer becomes a distant ceiling. It becomes family. The same laws that cool a cup of tea govern the evolution of galaxies. The same gravity that allows an apple to fall quietly shapes enormous clusters of stars. The same atoms drifting through frozen nebulae eventually became forests, rivers, birds, people. there is remarkable unity hidden beneath extraordinary scale. Perhaps that is why looking upward often produces both humility and comfort at the same time. We feel small, yet we also feel connected. Modern astronomy continues revealing new surprises almost every year. The James Webb Space Telescope peers farther into cosmic history than any previous observatory. Planetary missions continue preparing to explore icy moons. Radio telescopes quietly map invisible hydrogen stretching across enormous distances. New discoveries refine old ideas. Fresh questions replace comfortable assumptions. Science never truly finishes. It listens, observes, adjusts, learns. The universe remains generous enough to keep offering mysteries. Equally remarkable is what has not changed. The oldest light still fills every direction. Gravity still gathers clouds into stars. Entropy still guides warmth toward balance. The same elegant physical laws remain faithful across billions of years and trillions of kilometers. There is deep reassurance in such consistency. Imagine hearing the same gentle melody throughout every season of your life. Different instruments may play it. The tempo may change. Yet, the melody remains recognizable. Physics provides that melody. The universe composes endless variations. As we approach the end of tonight's journey, it becomes tempting to ask whether the coldest place in the universe has finally been found forever. The honest answer is beautifully simple. Perhaps, perhaps not. The Boomerang Nebula remains the coldest naturally observed location known today. Future discoveries may refine that understanding. Future observatories may uncover environments even stranger. Science welcomes such possibilities. Truth grows stronger when challenged by new evidence. That humility keeps discovery alive. And perhaps humility is the greatest lesson the universe offers. Not because humanity is insignificant, because reality is wonderfully larger than our imagination. Every generation inherits questions from those before. Every generation answers only a few, then quietly leaves new mysteries behind. The conversation never ends. Outside your window tonight, countless stars continue shining across extraordinary darkness. Between them stretches an ocean of cold, older than every civilization, older than every mountain, older than every memory carried by our species. Yet inside one small corner of that immense silence, a warm planet circles an ordinary yellow star. Rain still falls. Trees still grow. People still gather around tables. Children still laugh. Someone somewhere is reading a book beneath a quiet lamp. Someone else is watching snow drift through the night. Life continues because warmth still survives here. That warmth is precious precisely because the universe contains so much cold. Contrast gives meaning. Night gives beauty to sunrise. Winter gives gratitude to spring. Silence allows music to breathe. Distance teaches us the value of home. Perhaps that is why the coldest places in the universe never leave us feeling hopeless. Instead, they quietly remind us how extraordinary our small warmth truly is. And as you settle a little deeper into comfort, allowing your thoughts to drift as gently as ancient starlight crossing the darkness, remember one final truth. The universe has spent nearly 14 billion years slowly cooling, yet somehow, within all that patient silence, it created stars, then planets, then oceans, then life, then someone able to look upward, wonder about the cold, and finally understand that even the deepest darkness carries the faint, enduring echo of warmth. The room is quiet now, perhaps quieter than when we first began. The air feels familiar. Your breathing has settled into an easy rhythm, somewhere beyond the walls. The earth continues turning beneath the night sky, exactly as it has for billions of years. You cannot feel that motion, yet every second carries you gently eastward. Every minute carries our planet a little farther around the sun. Every hour carries the entire solar system a little farther around the center of the Milky Way. Even while resting, you are traveling, always, quietly, tonight. We began with something ordinary, a warm room, a human hand, a cooling cup of coffee, simple moments that belong to everyday life. From there, we drifted outward, past the frozen winters of Earth, past the silent plains of Pluto, past the sleeping chemistry of molecular clouds, past Europa's hidden ocean, past the ancient messengers we call comets, past the lonely voices of Voyager, past the oldest lights still crossing the universe. At every step, the same lesson returned. Heat moves. Cold remains patient. Time remembers everything. Perhaps the greatest surprise was not discovering how cold the universe truly is. It was discovering how rare warmth has always been. Our sun feels ordinary because it is familiar. Yet every sunrise represents an extraordinary victory against surrounding darkness. Every green leaf quietly captures energy that traveled 150 million kilometers across empty space. Every heartbeat depends upon that journey. Every conversation, every memory, every dream. Imagine lighting a single candle inside an enormous cathedral after sunset. The flame cannot illuminate every corner. Vast shadows still surround it. Yet everyone standing nearby immediately notices the warmth. The universe resembles that cathedral. Stars are its candles. Planets are the small circles of light surrounding them. Life gathers wherever enough warmth survives, long enough for complexity to bloom. The darkness never disappears. It simply waits beyond the light. There is something deeply reassuring about this picture. We often imagine ourselves struggling against an indifferent universe. Yet the universe never promised endless comfort. It offered possibility instead. Gravity gathered clouds. Cold preserved chemistry. Stars forged heavier elements. Planets assembled. Water flowed. Life awakened. None of these chapters required certainty. Only patience. Only time. Even now, astronomers continue searching for answers. New telescopes observe galaxies formed astonishingly early in cosmic history. Spacecraft prepare to explore icy moons. Radio arrays map invisible hydrogen stretching across unimaginable distances. Every discovery expands our understanding while revealing new mysteries waiting just beyond the horizon. That is the nature of genuine science. Every answer opens another question. Every question invites another journey. The universe never becomes smaller as we learn. It becomes richer, more detailed, more subtle. There is quiet wisdom hidden within that process. Human life often feels uncertain. Plans change, seasons change, people change. Sometimes uncertainty feels uncomfortable. Yet the cosmos reminds us that uncertainty is not the opposite of understanding. It is the doorway that allows understanding to continue growing. The oldest astronomers looked upward with only their eyes. Today, humanity observes the universe across radio waves. Infrared light, X-rays, gamma rays, gravitational waves, and exquisitely sensitive spacecraft drifting billions of kilometers from home. Tomorrow's discoveries will almost certainly surprise us again. That possibility is something to cherish, not to fear. If the universe has taught us anything tonight, it is that reality often proves gentler than imagination. The coldest places were not empty prisons. They were nurseries, archives, shelters, time capsules. The darkest regions were not meaningless voids. They carried ancient light, ancient chemistry, ancient memory. Even silence contained a story. Perhaps we can borrow that lesson for ourselves. There are seasons in every life that resemble winter. Moments when progress feels invisible. Moments when nothing seems to change. Yet frozen lakes still hide moving water. Sleeping forests still prepare for spring. Molecular clouds still gather future stars. Silence does not always mean nothing is happening. Sometimes the deepest transformations occur where no one is watching, including ourselves. As Earth continues its quiet orbit tonight, our planet remains astonishingly small compared with everything we have explored. Yet small does not mean insignificant. A single seed becomes a forest. A single note begins a symphony. A single photon crossing billions of years eventually reaches a telescope and changes humanity's understanding forever. Small things matter. They always have. Somewhere far beyond Neptune, ancient comets continue drifting through darkness. Somewhere beyond the heliosphere, Voyager still moves between the stars. Somewhere inside a cold molecular cloud, gravity quietly gathers another future sun. Somewhere within a distant galaxy, another civilization may be looking toward its own night sky, wondering similar questions beneath the same ancient background light. We do not know, and it is perfectly acceptable not to know. Wonder survives best when accompanied by honesty. The universe owes us no easy answers. It has already given us something even more valuable, a place within its story. As your thoughts become lighter, imagine the night sky once more, not as an empty ceiling, not as a frightening abyss, but as an immense ocean, calm, patient, timeless. Its cold stretches farther than imagination. Its silence reaches deeper than language. Yet scattered across that tranquil darkness are small islands of warmth, stars, worlds, moments, lives. You are living upon one of them. And perhaps that is the quiet miracle we were searching for from the very beginning. The coldest places in the universe did not teach us to fear the darkness. They taught us to appreciate every small source of warmth, every sunrise, every shared smile, every peaceful evening, every slow breath. Because against the patient backdrop of cosmic winter, even the gentlest warmth becomes extraordinary. And so, as the stars continue their silent vigil above, and the universe keeps drifting toward a future almost beyond imagination, you may let your own thoughts drift just as gently. There is nowhere else to travel tonight. The oldest light is still arriving. The coldest places are still waiting. The universe is still quietly unfolding. And for this brief, beautiful moment, you are home beneath its endless sky.